grounding bushing is indeed required in this scenario. Regarding the cable size for the grounding bushing, the minimum cable size is determined by the size of the grounding conductor attached to the bushing itself. According to the National Electrical Code, specifically Table 250.122, you can find the minimum cable size requirements for grounding bushings. For example, if the ungrounded supply conductors are 1100 amps copper or 1750 amps aluminum, the grounding electrode conductor size is 3/0. A common minimum cable size for grounding bushings is number 8 American wire gauge copper or larger. However, Table 250.122 provides the complete guide. The grounding conductor attachment is also critical. The grounding conductor must be securely attached to the grounding bushing using listed compression or bolted fittings. Ensure you use fittings that are specifically listed for grounding purposes. The grounding conductor should be sized according to the requirements outlined in the National Electrical Code Article 250.120. This article covers the proper sizing and installation of grounding electrode conductors. There are a number of additional considerations to keep in mind. Firstly, the grounding bushing should be installed strictly according to the manufacturer's instructions. These instructions provide specific details on how to properly install the bushing and ensure a secure connection. Secondly, the conduit must be properly bonded to the grounding system using listed bonding devices. This bonding ensures a continuous electrical path and helps to prevent voltage differences. Thirdly, the ground loop system should be inspected and tested periodically to ensure proper continuity. This regular inspection and testing helps to identify any potential issues and ensure the system is functioning correctly. Here's a more detailed breakdown of NEC Table 250.122, which is crucial for determining the correct grounding conductor size. This table correlates the size of the ungrounded conductors or equivalent area for parallel conductors with the minimum size of the grounding electrode conductor, whether it's copper, aluminum, or copper-clad aluminum. Firstly, if the size of the ungrounded conductors is number 2 American wire gauge or smaller copper, or number 1/0 American wire gauge or smaller aluminum, the grounding electrode conductor size should be number 8 American wire gauge copper or number 6 American wire gauge aluminum. Secondly, if the size of the ungrounded conductors is number 1 American wire gauge or number 1/0 American wire gauge copper, or number 2/0 American wire gauge or number 3/0 American wire gauge aluminum, the grounding electrode conductor size should be number 6 American wire gauge copper or number 4 American wire gauge aluminum. Thirdly, if the size of the ungrounded conductors is number 2/0 American wire gauge or number 3/0 American wire gauge copper, or number 4/0 American wire gauge or 250 kc mil aluminum, the grounding electrode conductor size should be number 4 American wire gauge copper or number 2 American wire gauge aluminum. Fourthly, if the size of the ungrounded conductors is 4/0 American wire gauge or 350 kc mil copper, or 300 kc mil or 500 kc mil aluminum, the grounding electrode conductor size should be number 2 American wire gauge copper or number 1/0 American wire gauge aluminum. Fifthly, if the size of the ungrounded conductors is over 350 kc mil through 600 kc mil copper, or over 500 kc mil through 900 kc mil aluminum, the grounding electrode conductor size should be number 1/0 American wire gauge copper or number 3/0 American wire gauge aluminum. Sixthly, if the size of the ungrounded conductors is over 600 kc mil through 1100 kc mil copper, or over 900 kc mil through 1750 kc mil aluminum, the grounding electrode conductor size should be number 3/0 American wire gauge copper or number 250 kc mil aluminum. Seventhly, if the size of the ungrounded conductors is over 1100 kc mil copper or over 1750 kc mil aluminum, the grounding electrode conductor size should be number 250 kc mil copper or number 350 kc mil aluminum. Note that where multiple sets of service entrance conductors are used as permitted in 230.40, exception number 2, the equivalent size of the largest service entrance conductor shall be determined by the largest sum of the areas of the corresponding conductors of each set. Where there are no service entrance conductors, the grounding electrode conductor size must not be less than given in this table for the largest ungrounded conductor. Also, the grounding electrode conductor must not be required to be larger than number 3/0 American wire gauge copper of 250 kc mil aluminum. Where connected to made electrodes as in 250.53c, that portion of the grounding electrode conductor that is the sole connection to a single or multiple rod, pipe, or plate electrodes must not be required to be larger than number 6 American wire gauge copper wire or number 4 American wire gauge aluminum wire. It's essential to consult the latest edition of the National Electrical Code, as codes and standards are updated periodically. Always refer to the specific requirements of the NEC and any local amendments that may apply in this specific jurisdiction. Here's a review on how to properly install a grounding bushing. Firstly, select the correct size grounding bushing for the conduit. Ensure the bushing is appropriately sized for the diameter of the conduit and that it is listed for grounding purposes. Secondly, clean the conduit threads. Remove any burrs, rust, or other debris from the conduit threads to ensure a good electrical connection. Thirdly, apply antioxidant compound. Apply a thin layer of antioxidant compound to the conduit threads and the grounding bushing threads. This compound helps to prevent corrosion and improve the electrical connection. Fourthly, install the grounding bushing. Screw the grounding bushing onto the conduit threads, tightening it securely with a wrench. Ensure the bushing is making good contact with the conduit. Fifthly, attach the grounding conductor. Connect the grounding conductor to the grounding bushing using a listed compression connector or bolted fitting. Ensure the connection is tight and secure. Sixthly, torque the connection. Torque the connection to the manufacturer's specifications to ensure a reliable electrical connection. Seventhly, protect the connection. If the connection is exposed to moisture or corrosive elements, protect it with a suitable sealant or tape. Eighthly, inspect the installation. Visually inspect the installation to ensure that all connections are tight and secure, and that the grounding bushing is properly installed. A proper ground loop system is a continuous conductor encircling a building or facility, typically bonded to the building's structural steel and other grounding electrodes. It serves as a low impedance path for fault current, enhancing the effectiveness of the grounding system. Firstly, the primary purpose of a ground loop is to provide a low impedance path for fault currents, facilitating the quick operation of overcurrent protective devices such as circuit breakers and fuses. Secondly, the ground loop helps to equalize the potential between different points within a building, reducing the risk of electrical shock and minimizing the effects of electromagnetic interference. Thirdly, by bonding the ground loop to the building's structural steel, it creates a comprehensive grounding network that helps to protect equipment and personnel. The components of a ground loop system include the main grounding conductor, bonding jumpers, grounding electrodes, and connection methods. The main grounding conductor is typically a large diameter copper conductor that encircles the building. Bonding jumpers are used to connect the ground loop to the building's structural steel, metallic piping, and other conductive elements. Grounding electrodes, such as ground rods or ground plates, are used to connect the ground loop to the earth. Proper connection methods, such as exothermic welding or listed connectors, are essential for ensuring a reliable electrical connection. Firstly, the ground loop should be installed in accordance with the requirements of the National Electrical Code NEC Article 250. Secondly, the size of the grounding conductor should be determined based on the size of the service entrance conductors. Thirdly, the ground loop should be bonded to the building's structural steel at multiple points. Fourthly, the ground loop should be connected to grounding electrodes that are installed in accordance with NEC requirements. Fifthly, all connections should be made using listed connectors or exothermic welding. There are a number of inspections and maintenance steps one can take to ensure a proper ground loop system. Firstly, visually inspect the ground loop and its connections regularly for any signs of damage or corrosion. Secondly, test the continuity of the ground loop using a ground resistance tester to ensure that it provides a low impedance path for fault current. Thirdly, verify that all bonding connections are tight and secure. Fourthly, inspect the grounding electrodes to ensure that they are in good condition and properly connected. Fifthly, keep records of all inspections and maintenance activities. To further illustrate how to determine the grounding electrode conductor size using NEC Table 250.122, let's consider a few practical examples. Example 1. If the ungrounded service conductors are two parallel sets of 500 kc mil copper conductors, the equivalent area is 1000 kc mil. According to Table 250.122, the minimum size of the grounding electrode conductor is number 3/0 American wire gauge copper. Example 2. If the ungrounded service conductors are 4/0 American wire gauge aluminum, the minimum size of the grounding electrode conductor is number 2 American wire gauge aluminum. Example 3. Consider a situation where the ungrounded conductors are two parallel runs of 300 kc mil aluminum. The combined size would be 600 kc mil aluminum. Referring to NEC Table 250.122, the minimum grounding electrode conductor size would be number 3/0 American wire gauge aluminum. Remember, these examples assume you are connecting to a grounding electrode system as described in NEC 250.50. If you are connecting to a single rod, pipe, or plate electrode, the conductor size may be different as noted earlier. To elaborate on grounding conductor attachment, it's important to use methods and materials that ensure a reliable, low-impedance connection that can withstand fault currents. Firstly, use listed connectors. Always use connectors that are listed and labeled for grounding purposes. These connectors are designed and tested to meet specific standards for conductivity, mechanical strength, and corrosion resistance. Secondly, compression connectors. Compression connectors provide a secure and reliable connection by crimping the connector onto the conductor with a specialized tool. Ensure the correct die and tool are used for the size and type of conductor and connector. Thirdly, bolted connections. Bolted connections are another option, but they must be properly torqued to ensure a tight connection. Use star washers or other locking hardware to prevent loosening due to vibration or thermal expansion and contraction. Fourthly, exothermic welding. Exothermic welding, also known as CAD welding, creates a permanent molecular bond between the conductor and the grounding electrode. This method is often used for critical grounding connections where reliability is paramount. Fifthly, surface preparation. Before making any connection, clean the surfaces of the conductors and connectors to remove any dirt, grease, or corrosion. A wire brush or emery cloth can be used for this purpose. Apply an antioxidant compound to the clean surfaces to prevent future corrosion and improve conductivity. Sixthly, torque specifications. Follow the manufacturer's torque specifications for all bolted connections. Under-torquing can result in a loose connection, while over-torquing can damage the connector or conductor. Use a calibrated torque wrench to ensure accurate tightening. Seventhly, protection from corrosion. Protect the completed connection from moisture and corrosion by applying a suitable sealant or tape. This is especially important in harsh environments where the connection may be exposed to chemicals, salt water, or other corrosive substances. By following these best practices for grounding conductor attachment, you can ensure a safe and effective grounding system that protects equipment and personnel from electrical hazards. A grounding bushing is a specialized fitting used to provide a low-impedance path for ground fault currents, typically used when a metal conduit enters an enclosure. Here are some key features of grounding bushings. Firstly, material construction. Grounding bushings are typically made of metallic materials such as aluminum or bronze, providing excellent conductivity. Secondly, the insulated throat. Many grounding bushings feature an insulated throat to protect conductors from abrasion as they pass through the bushing. Thirdly, lay-in lug. Grounding bushings often have a lay-in lug that allows the grounding conductor to be easily inserted and secured. Fourthly, set screw. A set screw is used to securely attach the grounding bushing to the conduit, ensuring a reliable electrical connection. Fifthly, listed. Grounding bushings should be listed by recognized testing laboratories such as Underwriters Laboratories UL to ensure they meet safety standards. By understanding these key features, you can select the appropriate grounding bushing for specific applications and ensure a safe and effective grounding system. The purpose of bonding is to create a low impedance path for fault current back to the source, allowing overcurrent protection devices to quickly trip and clear the fault. Grounding and bonding work together to provide a safe electrical system. Firstly, bonding connects non-current carrying metal parts of an electrical system together, while grounding connects the system to the earth. Secondly, bonding ensures that all metal parts are at the same electrical potential, reducing the risk of electric shock. Thirdly, grounding provides a path for fault current to flow back to the source, allowing overcurrent protection devices to trip and clear the fault. Fourthly, proper bonding and grounding are essential for protecting equipment and personnel from electrical hazards. Fifthly, the National Electrical Code NEC provides detailed requirements for bonding and grounding electrical systems. By understanding the relationship between bonding and grounding, you can design and install electrical systems that are safe and reliable. To summarize the grounding and bonding requirements outlined in NEC Article 250, it covers the general requirements for grounding and bonding electrical systems to ensure electrical safety. Here's a breakdown. Firstly, grounding electrode system. NEC 250.50 requires that all grounding electrodes that are present at each building or structure served be bonded together to form a grounding electrode system. This system typically includes items such as metal underground water pipes, metal building frames, concrete encased electrodes, and ground rings. Secondly, grounding electrode conductor. NEC 250.66 provides requirements for the size of the grounding electrode conductor. The size is based on the size of the service entrance conductors. However, it also specifies that the grounding electrode conductor is not required to be larger than number 3/0 American wire gauge copper or 250 kcm aluminum when connected to rod, pipe, or plate electrodes. Thirdly, bonding of metal enclosures. NEC 250.92 and 250.96 cover the bonding of metal enclosures and other metal parts of the electrical system. These sections require that metal enclosures containing service conductors and equipment grounding conductors be bonded together to create a low impedance path for fault current. Fourthly, equipment grounding conductors. NEC 250.118 lists the types of equipment grounding conductors that are permitted, including wire-type equipment grounding conductors, metal raceways, and cable trays. These conductors must be sized according to NEC 250.122, based on the rating of the overcurrent protective device in the circuit. Fifthly, methods of grounding. NEC 250.130 outlines the methods for grounding equipment, including the use of equipment grounding conductors, bonding jumpers, and grounding electrodes. It also provides specific requirements for grounding different types of equipment, such as receptacles, lighting fixtures, and appliances. Sixthly, separately derived systems. NEC 250.30 provides requirements for grounding separately derived systems, such as generators and transformers. These systems must be grounded in accordance with the requirements of Article 250, including the installation of a grounding electrode system and the bonding of metal enclosures. Understanding these key requirements of NEC Article 250 is essential for designing and installing safe and effective electrical systems. Always refer to the latest edition of the NEC and consult with a qualified electrical professional when working on electrical projects. Ground loops are typically used in sensitive electronic equipment to minimize noise and interference. It's also critical in larger buildings to have ground loops. Here's a review of the types of grounding systems. Firstly, single-point grounding. In a single-point grounding system, all ground connections are made to a single point, minimizing the potential for ground loops. This type of grounding is commonly used in sensitive electronic equipment. Secondly, multi-point grounding. In a multi-point grounding system, ground connections are made at multiple points throughout the system. This type of grounding is often used in larger buildings and facilities. Thirdly, hybrid grounding. A hybrid grounding system combines elements of both single-point and multi-point grounding, providing a balance between noise reduction and fault current protection. The choice of grounding system depends on the specific application and the level of sensitivity to noise and interference. A ground loop creates a continuous path for current to flow in a grounding system, which can lead to noise and interference. Here are a few common grounding mistakes. Firstly, improper grounding conductor size. Using an undersized grounding conductor can limit the effectiveness of the grounding system and increase the risk of electrical shock. Secondly, loose connections. Loose connections can increase the impedance of the grounding path and reduce its effectiveness. Thirdly, improper bonding. Improper bonding of metal enclosures and equipment can create ground loops and increase the risk of electrical shock. Fourthly, failure to test the grounding system. Failure to test the grounding system after installation can result in undetected problems and increase the risk of electrical hazards. By avoiding these common grounding mistakes, you can ensure that the grounding system is safe, effective, and reliable. Finally, remember to review the manufacturer's instructions. Always follow the manufacturer's instructions for installing and maintaining grounding equipment. The grounding bushing is a very important aspect to the design and system.